find that these do not have to be real, since it wasn't a Hermitian matrix to begin with. But you can always, since there's some phase arbitrariness in these matrices, and you can use that so that they can become real and positive. Okay, so let me construct these matrices, and then I can rewrite this. And because this is the identity and this is the identity, and this is just minus d bar left md diagonal d right, where this is what I mean by d diagonal. And d left, which is d s or b left, is just a l d dagger. D 0 left and d right, d s d right is a right d dagger d 0. Right. So a right dagger d right is d right, and the adjoint of all this gives you d bar left. Let me also insert my 1 plus h over mu here. So I have simply minus, and there's also always a Hermitian conjugate. So I have some I equals d s and d of mi d bar I left d I right times 1 plus h over mu plus Hermitian conjugate. Now I've written out the diagonal matrix explicitly. And of course, math terms for fermions are always of the form psi bar left, psi right, plus the Hermitian conjugate is psi bar right, psi left, and that's just psi bar psi. So I have finally equals minus some, so the Yukawa, L Yukawa becomes minus some over I equals d s d of mi d bar d times 1 plus h over. So this is a math term for each enters an I-ness. So these are just the math terms for the downstream and bottom quarks, and we've chosen any necessary phases in these A's so that they are real and positive. And so we generate masses for the down quarks, and similarly for the up quarks and the electrons and the neutrinos. At least one way of generating masses for the neutrinos. So not only that, we have also generated Yukawa couplings. Not only have we generated mass terms, but we've generated Yukawa couplings, which are so here's the I quark, I down quark, and here's the H. And the coupling is like I times the Lagrangian, so the coupling is simply minus I times the mass divided by the weak scale, 246 GeV, and that's it. So the Higgs couples to the fermion. It's a scalar, there's no gamma 5, and it's proportional to the mass of the quark divided by nu. And nu, if I didn't write it, yeah, I wrote it up there. So if the quark is very light, or like the down quark, then, or the electron or whatever, then this is very tiny. But if one's talking about the top quark, which is very heavy, then it's a big coupling. And we saw something similar for the couplings to the W and T, which were also proportional to the mass squared, in that case, of the H boson. So the Higgs actually couples proportional to mass. Any questions so far? So, couples proportional to mass. That's not surprising, because the Higgs mechanism generates the mass. And that's a function of the fact I had only one Higgs doublet, one gamma d, and whatever diagonalized the gamma d for the masses simultaneously diagonalizes for the Higgs coupling. And that's very important. There are no transitions, such as you might have had S goes to D, for example. That would be a flavor not diagonal. And if there were such a thing, then you could have on the other side, you could have, for example, D bar, S bar. So this would be an S to D bar and a D to S bar. So this would take S D bar goes to D S bar. And we'll see later that this is disaster. Such processes are observed in nature, but they go in second order weak. And if if they had gone by this, they would have been far too large. Yes.
So why would you choose UCD to use the basis slightly far lower basis on the flavors as like weak basis? I guess you use the mass basis as opposed to weak basis.
In QCD, well, let me just make one other comment. I said couples to mass. If you have a non-chiral fermion, then it would have an elementary mass, and that wouldn't be a problem. Okay, now, in QCD, I'll give you two answers. One is that if you're just talking about QCD all by itself, then you could have had, pretending that was the theory of the world, then in the downport sector, you could have just as well had something that was sum I equals 1 to 3, d bar I0 d u slash di. This is not a QCD covariant derivative. Minus sum from ij equals 1 to 3 of d bar I0 m ij dj0. I could have written that perfectly consistent with QCD. In that case, the very first thing I would have done on line 1 is to diagonalize this matrix using the same separate left and right. So that, and then those matrices wouldn't have entered anywhere else if I were just talking about QCD, and I would just work in that basis. So really, it didn't have to be diagonal, but diagonalized to begin with. The second answer is that if you're considering the real world, then you're really considering SU3 cross SU2 cross U1 simultaneously. And the QCD masses are really these guys generated in the by L-Upala in what I've been calling the weak sector, but it's all one theory. So the first stage is you generate the masses this way, diagonalize, and then you're there. Okay, I just wanted to say that I will come back to these transitions later, briefly at least, and this goes under the name K0 bar fixing. And this is actually the K0 bar state, which strange is -1, and this is the K0 state, which strange is +1. And there are transitions between it observed in nature, but they're very tiny. And this one, if it had been present with any appreciable strength here, would have been disastrously large. Similar stories apply in the gauge sector without if you didn't have a term book. But fortunately, with a single Higgs doublet, there's no favor off diagonal thesis. In the MSMM, there are two Higgs doublets, but one doublet couples to the down quarks and the other only to the up quarks. So in each sector, there's only one, and the same thing happens. But in generalization, this is the standard model. With extra Higgs doublets, this is a real constraint, a real problem, avoiding the flavor changing vertices. Okay, now let me say a word about the eigenvalues and eigenvectors. The eigenvalues that we observe, this is from experiment now, and I'm going to write them for all sectors. Okay, so this is actually about 2 MeV, and this is about 5 MeV. Not 300 MeV, which you would have guessed. It's just a very tiny amount. The down quark's a little bit heavier than the up. That's why the neutron is heavier than the proton. Most of the mass of the proton is from dynamical QCD effects, not from these masses. And these are so tiny, and that's why we say there's an almost chiral SU2 isospin of the strong interactions. The isospin symmetry is not so much because these are nearly degenerate, they're not. Except they're both so close to zero that they don't much matter. The electron is about half an MeV. The charm quark is about 1.3 GeV. 1.3, so this is almost 1,000 times heavier. And the strange quark is about 105 MeV. And the muon is 100, no, I'm sorry, the strange quark is about 100, let's say 100. And this is about 105 MeV. This is about 174 GeV. So it's much heavier than, it's even heavier than the W and Z, twice as heavy, and almost at the electroweak scale. This is about 5. And this is about 1.8. So nobody understands this pattern. This is very light, this is intermediate, this is much heavier. For all the quarks have a mass of about 300 MeV just from the QCD stuff that has nothing to do with this, and most of the proton mass comes from that. This mass difference breaks isospin. The fact that S is 100 MeV in the case of the SU3. The global SU3 is broken, right, because of that. And that's sort of typical of mass splittings. Big small numbers come from the pion mass, which remember was an almost full-stone boson with the chiral symmetry there. So anyway, that's what we observe. The whole pattern, why this is so much heavier, and then the splittings within, like even within this family, there's a factor of 10 here between this and these, and there's a big difference between these and nobody understands this pattern. So that this is a flavor, or half of what's called a flavor problem. There's nothing inconsistent about it, it's just we don't understand it. It's not like the gauge sector where things are constrained, and it's all these matrices were arbitrary. Yes?
There, so I think argument was
there are anthropic arguments, especially here and here. Basically, if you want to have a complicated chemistry, you need a complicated spectra of nuclei, some of which are stable and others are unstable. And if you fiddle with these masses very much, you wouldn't, like for example, if the up quark were heavier than the down quark, then let me put it a different way. If the down quark were much heavier than the up quark, then you wouldn't have light nuclei. Everything would just turn into neutrons. How compelling those arguments are, I don't know. And nobody's given it. I mean, these heavier families don't seem to play much role in ordinary nature. About the only quasi-anthropic argument anyone's given for these is that you need these to have CP violation, and you need CP violation to have more matter than antimatter. Anything else? Okay, let me now to the other half of the problem, though, because I'm not. I want to rewrite my weak interactions in terms of these guys. So I go. So we saw yesterday that the weak charge current, well, it was L equals minus G over 2 root 2 J mu W mu minus plus J mu dagger W mu plus. And the charge raising current was the sum of M equals 1 to 3 of U bar M0 gamma mu 1 minus gamma 5 E M0 plus U bar M0 gamma mu 1 minus gamma 5 T M0. This is the weak interaction basis. It's by definition diagonal because you got 3, 4, actually 2 doublets, and we just label the 3 doublets as 1, 2, 3. By definition, the transitions are just with the states. However, we've seen that the DL0 is ALD times the mass eigenspace, and similarly, the UL0 is related to some mass eigenspace by a different unitary transformation, AU, and similarly even for the others. I'm sort of pretending now that the neutrinos are just like everything else. On Thursday I will talk about other possibilities, but I'm not focusing on neutrinos at this point. So I have to rewrite this in terms of the mass eigenspace, and it becomes Kobayashi-Masawa is just given by A-L U dagger ALD and V sub L for lepton, which is called the PM in S matrix on the Korbo, Maki, Nakagawa, Sakai. Actually, for some weird convention, there's a dagger here. That's equal to AL U dagger ALE. In other words, let's just focus on this one. These states are different from these. They're two different states merely connected by the weak interaction.